Hello everyone. Today I'll be explaining why do we use activation functions. So you must have heard about activation functions like Sigmoid, and then there is Tanh, there is ReLU, leaky ReLU, SILU. So why do we use these activation functions? And how does the shape of the activation function affect our model? First, we have a very simple model, a neural network, which is basically two linear layers, 1, 64, 64, 1. Basically, it should look like this: 1, 64 points, and then 1. So this is our network, and we can choose to add a activation function in between or not. Okay, first we will not have the activation function. The activation function I plan to demonstrate is the sigmoid function. So we have the model. We are just giving it a input of 1 to 10. Now let's plot the output, and we can see it's a linear line. Okay, but this is not linear regression. This is a neural network. So let me demonstrate this with a more sophisticated data set, which is the diabetes data set. We will primarily be using the BMI. This is to make understanding this easier because multiple features, the dimensionality makes it harder to visualize. We initialize the model and we give it the data. And we plot our model relative to the data. So this model right now is not trained, and that's why it makes a line, but it's not perfect. Now let's train the model. This is our training function. Now if we train the model, as you can see, it's training, and we have a line that's now better fit to the training data. But you can see that it's still a linear line. It's straight. At the end of the day, the linear layer, the dense layer, the neural network, it's just a linear transformation. Because essentially what we have is just a linear transformation. Let's see. We have the batch size 16. That means, and we are giving it input dimension of 1 because we are only using one feature, BMI. So the input is going to look something like this: 16 batch size and 1 the input dimension. This is our input. Now it's going to be multiplied with the weight of the first layer. The first layer is going to have dimension of 1, the input dimension, and 64, the number of hidden layers, as we have specified over here. Now these two are going to have a dot product between them, and the output, it's going to be another matrix, which is 16, 64. Now this is the output of the first layer. Now this output is going to be fed into the next layer, which means it's going to be the input for the next layer. Now this is gonna get multiplied by another matrix, the weight matrix. Oh, I forgot to add the biases. You have to know that there will be biases. We did not disable the biases, but for simplicity we don't necessarily need to consider the bias that often. This is the basic mathematics behind the initial model. Now what we are gonna do is we are gonna add an activation function. And basically it's gonna go, the input is gonna go through the activation function into the next layer. Let's see how that looks. So we have the trained line to the model. Now we will initialize the same model, but we will include the sigmoid. Let's compile that. Next we are going to train the model again. We are doing the same thing, it's the same function, it's the same process, but we will get a different result. Let's look at the loss of the last model, which was 0.6637, and the new loss is 0.6616. It's less. Why is it less? It's less because if you look at the line made by the model, you can see that it's a slope. It's a slight slope. Now, does this look familiar? We are using a sigmoid. And how does the sigmoid function look? So the shape of the activation function is how it will affect the model graph. Now, let's try something else. We are going to use ReLU. ReLU is one of the most popular activation functions used. It's used with convolution, transformers. So let's see how ReLU performs in this model, this data set. 0.6637, 0.664. Again, it's slightly less than the linear no activation. Now you can see the line projected by the model is very, what should I say, it's geometric. And that's how ReLU divides up the data into two sections. Because of this geometric shape, many models prefer to use ReLU. So because ReLU cuts through the data in such a sharp manner, and it's all because of the shape of the ReLU activation function. As you can see, it's a straight line, and because of that, you get all these geometric shapes. Now, you might be thinking, should I use activation functions everywhere? Not necessarily. Activation functions are just a way to introduce non-linearity in linear transformation. So originally, because a neural network architecture is just basic matrix multiplication, it's just linear transformations, they will not be able to learn complex patterns. But because you want a deep learning model to learn all these complex patterns, you introduce activation function when you want a model to recognize complex patterns. So this means most models will have a non-linear activation function at the end of a linear transformation. This means dense layers, convolution, Convolutions are also a linear transformation. So, to summarize, activation functions are nonlinear functions introduced in a model to make the model recognize or fit itself to a dataset in a nonlinear way. Because this is fine, but this is better. And that's why we use activation functions. That's all from me. Goodbye.